one of only 2 days all year where our colors are actually useful.
Exactly.
What's the other day?
Ooh, graduation.
Okay.
So this is the cultural question for today. And there's also a handout, which
Ooh,
yeah,
I like it.
yes. So who has seen the Dr. Seuss Cat in the Hat?
Is in the book or the movie?
Because
I don't count the movie.
The book is
well,
way better than
it depends which movie you're talking about.
The recent movie?
The recent movie was unacceptable.
I think there was like an old cartoon.
There was an old cartoon with
Right,
Alan
yeah,
Sherman
okay.
from the 60s, and that one was funny.
Yeah, okay.
Alright. So, cultural question for today. Who can tell me where the Cat in the Hat went to school?
Is there another Princeton? One of
I'm
No.
gonna go with UCSD.
No. UCSD?
They've got the guys' library.
You're close. It sounds like a California institution.
Sound?
Nobody knows where the Cat in the Hat went to school?
Oh, it's gonna be a pun.
It's going to be a
Okay.
pun. A pun on a California school. So you can be thinking about that and pondering it during today's lecture. But like the real Cat in the Hat, there's also goodies in the hat. Now, unfortunately, you are the second class today, so 341 has heavily hit into it. But we had a lot. Yeah. So this is why you don't sit over there on the left. So between 341 and the trick-or-treaters, there's not much left, but whatever is left, by all means, go for it. We have a new policy inspired by Philippe, who wants to be treated like my kids. So Cameron gets M&Ms when he answers math problems correctly. They don't have to be hard math problems. So to get you to email me when you make comments in class, I will start bringing M&Ms every day. If you send me an email for a comment you make in class, you may have 1 M&M per comment. Okay? So, put it in the bank right now. For the first time ever in 341, somebody actually lost an M&M comment that was so bad.
Ooh.
So if you want, you can actually watch the probability video. It probably will not be uploaded until Monday because I'm traveling and I don't know what kind of internet bandwidth the hotel will have. But yes, somebody actually lost an M&M for a comment they made in class. It was the first time ever in my career.
Give us like a background to this.
No. The video is there. You can watch it and learn some probability. Okay. So it looks like there should still be at least enough food for everybody. So I have forgotten my notes in my room, which will make today's lecture a little bit more interesting. Alright, so I'm pretty sure we wanted to talk about, or either wanted to or were supposed to talk about Montel 2. The greatest difficulty without having my notes is I forget how to spell Azella Ascoli.
You want me to get it?
No, it'll be more fun like this, Azella, but I appreciate it. I think it's something like that, Azella Ascoli. Is it all gone?
Well, there are 2 left.
Okay, did anybody else, did you want to leave?
I already had one.
Okay.
Girl, Philippe's here.
Ooh.
Oh, no.
No, go for it. Alright.
I don't even know what this is.
I'll get you a brown bag for your wine later.
Oh, thanks.
So, Azella Ascoli is the... Oh wait, did we prove the first part of Montel?
We didn't finish it.
We didn't, we just stated it. Okay.
There's
So,
one more piece.
so Montel 1. So for Montel 1, we have F is a family of holomorphic functions, right? What else were we assuming about the family? Uniformly bounded, a little bit more than uniformly bounded. Uniformly bounded, 2 more words. On compact. Then F is what? Excellent, you guys are doing phenomenal today. Already M&Ms will be flying out. Okay? So the question is, how do we prove this? And the other thing is the word holomorphic important? So in last class, we talked about what would happen if we just had bounded first derivative. And bounded first derivative was fine. But maybe if the first derivative exists but is not bounded, maybe there's a problem. So again, whenever you have a theorem, we move a condition and see what happens. Alright. But for today, we do have holomorphic functions. And so when you see holomorphic, what do you think of?
Taylor series.
So you think of Taylor series, that's one way to think about it. What else do you think of when you see holomorphic? infinitely differentiable, which will be related to the Taylor series. What else do you think about? If I give you a function that's holomorphic, what else do I know? It's continuous. Well, I want to show that the family is equicontinuous. So given an epsilon and a compact set, so I have to show the following. Given epsilon greater than 0, given compact k, there exists a delta which will depend on epsilon and k such that z minus w less than delta, then f of z minus f of w is less than epsilon for all f and f. And of course, I'm implicitly assuming that z and w live in k. This is what I need to show if I am equicontinuous. So I'm going to need to somehow deal with values of my function. Do you know any results that allow you to talk about values of a function? Cauchy. Cauchy's theorem. Why is Cauchy's theorem useful? What do we know? We're uniformly bounded on compactor. So Cauchy's theorem tells me the value at this point is related to an integral of my function. And I can say a little bit away from that point. And if I'm uniformly bounded, I can then bound the numerators in the Cauchy expressions. And now when I look at the differences, I should maybe somehow get a z minus w coming in when I subtract two Cauchy formulas. So, suggests using Cauchy, or Cauchy's theorem. We're not going to use Cauchy's body. Right? Could we do this for real variable functions?
No.
No, why not?
We don't have any theorem that tells
We don't have anything even close to this for real valued functions. So again, this proof is clearly going to be a complex analytic proof. Okay, so now the question is, which points do we look at and how do we look at them? What compact sets do we look at? So we have some compact set K. What I want to do is I want to be a little bit careful to make sure I stay inside a compact set where I'm uniformly bounded. That compact set doesn't have to be the same as this compact set. So here's the proof. We have, here's a big set omega. Here's some compact set K over here. If I have, a point on the boundary, if I try to draw like a little circle around this to do a Cauchy integral, I actually leave the compact set K. So I've got to be careful. Well, there's going to be a minimum distance between the boundary of K and omega. Why is there a minimum distance between the boundary of K and omega? I'm sorry? Not exhaustion. Why do I know there has to be a minimum distance between the boundary of K and the boundary of omega?
Because
Omega's open and K is closed.
Omega is open. The boundary of omega is going to be compact. Or is going to be a closed set. K is compact. So for each point on K, I can see its distance to the closed set that's the boundary. And then I can just use the result from analysis. A continuous function on a compact set attains its maximum minimum. So let 3r be less than the distance from K to the boundary of omega. So what I can do is, you give me any point in K, if I draw a circle of radius 3r, I'm still going to be within omega. And if I inflate this by drawing disks of radius 3r about every point, do I get a compact set? Yes. One way to see this is I only need finitely many of these disks to cover the initial set K. We can play lots of games. What I'm going to do is, you give me any point, I'm going to draw a circle of radius 2r about each point. And that's going to give me a little bit of freedom. So form the compact set K2R. And that's by drawing circles of radius 2R about each. So draw circles of radius 2R about each z and k. And that's going to give me a new compact set. And again, we assumed our family of functions was uniformly bounded on compactor. So we just have a new compact set, K2R. Now, let's see, if we have a K3R and a K2R, a KR is probably coming. We're looking at circles of radius R. Why do I want circles of radius R? That's going to be what I'm going to use for Cauchy's formula. And now when I draw a circle of radius R about each point, I know I'm going to stay inside K2R. So the reason I have to be careful is I need to make sure I stay in one specific fixed compact set. That's the difficulty. And if I just started working with K, and I just drew a circle about it and I made sure I stay inside omega, I could cut across into many different compact sets. I want to make sure that there's one compact set. I need a uniform bound that's independent of what compact, of which point I'm on. So now, draw a circle of radius R about points for Cauchy. Alright.
The points are in K, right? Not in K2R.
The points Z and W are going to be in K.
Okay.
But when I do the integration for Cauchy, the integration will be in K2R. Technically it's actually not in K2R, technically it's in what? I could have had something else. Instead of going all the way to K2R, I could stay in just what? KR. But I want to be very careful. What happens if I'm exactly on the boundary of something? Give yourself some wiggle room. Never have everything aligned so carefully that if somebody then finds a small mistake, you're in trouble. Give yourself a little bit of extra freedom. And so let me draw balls of radius 2R, and if I have something of radius R about that, I'm fine. The other thing, of course, is I want to figure out how close is Z to W. Maybe Z is a little bit far away from, maybe W is a little bit far away from Z. And then if I'm drawing a ball about radius W, maybe I could have some trouble. So what we're going to do is we're going to look at f of Z minus f of W. And we're going to assume Z is close to W. How close do you want to assume W is to Z? No! No. You've now lost an eighth of an M&M for me.
Oh no.
Yeah. 2 in a row. Why can't we ever talk about Z and W being epsilon apart?
You have to find it.
Wait, no. Why can't we do epsilon for Z and W?
Because we don't have a delta yet.
Right. We always use delta here. It's like switching the axes in economics between price and quantity. Right? Epsilon is never used for the distance between points. Right?
Okay.
We always use epsilon for the difference between the values of the function at those points. So the points Z and W should be within delta of each other.
Oh, I should talk about that.
No, I wrote that, but I asked you how close is Z and W.
Oh,
Alright, then you regained the M&M.
Okay.
You regained the M&M. So how close do I want Z and W to be? They want to be within delta. Now, we don't know anything about delta yet. Can you tell me something that's likely true about delta?
Less than R.
Delta is less than R. So, take delta less than R, assume Z minus W is less than delta. And again, we don't have to find the largest R that works. We just need to find the largest delta that works. We just need to find some delta that works. Why not just take delta to be less than R? Well, if we take delta to be less than R, then we know, so if here is Z, this is not going to be drawn to scale. Here's a circle of radius R, here's a circle of radius 2R, here's a circle of radius 3R. W would have to be inside that circle of radius R. And so, I have the following. 1 over 2 pi I integral along, I'll call it a closed curve of radius R about the point Z of f of zeta over zeta minus z minus f of zeta over zeta minus w. D zeta. And absolute values everywhere. So I'm just using the Cauchy integral representation. I can represent the value of my function at a point by doing a nice integration. And what's nice about this is the numerators I can bound. And I can bound independently of the points z and w. All that matters is that it's in the set, K2R. Well, 1 over z minus zeta could be small. That's good. But it could also be very large. 1 over z minus zeta, that could be a very large number, in which case this would not be making it small. Fortunately, I'm subtracting off 1 over zeta minus w. And these two should be very close to each other. And so when we do some of the algebra, we get that this is equal to 1 over 2 pi, the integral over gamma z. And now we'll have the absolute value of f of zeta. And now when we subtract, we get zeta minus w minus zeta minus z. So we get a z minus w divided by zeta minus z, zeta minus w, d zeta. And I'll put in absolute value.
Where did the I go?
I'm taking absolute values. And so we'll see if this works or if we have to shift things a little bit. So right now I'm just integrating about a circle of radius r about z. What can you tell me about the magnitude of zeta minus z?
Where's the
You can do a little bit better than at most r.
Less than
Nope. So I'm integrating about a circle of radius r about z. So what can you tell me about zeta minus z?
R.
It's r, right? I'm integrating about a circle of radius r about z, so zeta minus z is r. Alright, that's not so bad. What about zeta minus w?
Bounded by R.
It's bounded by r, but could it be smaller than r?
Yeah, it will be small.
Yeah, if w, in fact, has to be smaller unless w is exactly z, in which case this is not that hard to estimate. How small could zeta minus w be?
Minus delta. What's the mean?
Well, I want to know how small zeta minus w could be.
Because that's your circle, you see, so here, suppose W is over here, then that's the...
Okay, so I could look at it as r minus delta. And then if delta is really small, I will be okay. So, again, I know w is no more than delta away from z. Right now, I've just said delta is at most r. So this can't be more than r minus delta. And so if I do that, I'm okay. If I don't make any additional restrictions on delta, I could have some trouble. And that this could be very close to 0. If w is very close to the boundary. So there's a couple of things we can do. One is we can just make sure delta is small. So we took delta to be less than r. What can I take it to be less than? R over 2. Now if I take it to be less than r over 2, then this will be okay. Another thing is, rather than integrating over a circle of radius r, what could I integrate? 2r or 3/2 r. You have lots of different ways of doing the analysis. Okay? There's not one right way to do the calculation. I think the simplest one is to let's make it r over 2. So that looks like now r over 21. So if we just now assume that delta is at most r halves, now we know zeta minus w can't be too much. And so if I look at this, this will now be less than or equal to 1 over 2 pi. What is the perimeter of the circle? 2 pi r. How large can the absolute value of f of zeta be? Some number. It's going to be b of 2k, right? Because I'm using the bound from the set k2r. And now what about the zeta minus z, zeta minus w down here? This is exactly r.
R squared over 2.
I think it's r squared over 2. And I still have the z minus w. Okay. So when the dust settles, the 2 pi's cancel. One of the r's cancels there, and I get b2k times 2 divided by r times z minus w. And I want that to be less than epsilon, if z minus w is sufficiently small.
What is B2K again?
So, my function f is uniformly bounded on compact sets.
Oh, okay, so that's just going to be the boundary.
That's just going to be the boundary. In fact, I could probably get away with not b2k, but maybe b... I'm sorry. I'm sorry, I'm not calling it b2k, I'm sorry. I called the set k2r. So it should be sub k sub 2r. I think that's the notation I'm using, I apologize.
Right, notation would be put the bound plug the whatever that is then plug.
Exactly. So it's b for bound, and then the subscript is the set it's coming from. And the set it's coming from is the set k2r. I could probably get by with the set kr. I really don't feel like balancing on a typo and doing the calculations so carefully to see, can I just squeeze by? Let me give myself a little bit of extra leeway. Because does it matter? No. So give yourself a little bit of freedom. So I need this to be less than epsilon if z minus w is sufficiently small. Yes?
Sorry, backing up just a step.
Yes.
What did we replace zeta minus w with?
R over 2.
Okay, why did we... So why did we do that? Because we were saying this next expression is greater than or equal to, but isn't zeta minus w at least r, or is it at most r
It's
over 2?
At most, because w is within delta of z, and delta is now r halves. So if you want to think of it as, here's z, here's zeta, which is r units away, and here's my delta, which is my delta is within r halves.
So it's at least R.
So it's at least r over 2, away from the boundary. So I want this to be as small as possible to make this fraction as big as possible. The worst case for me is if zeta minus w has magnitude r halves. And so if it has magnitude r halves, that's the worst case. All I need to make sure is that zeta minus w can't get too small. And so now I need this whole thing to be less than epsilon. So above is less than epsilon if z minus w is less than what? Excellent. R over 2bk2r times epsilon. And again, so what I can really do is this tells us to take delta to be less than the minimum of r halves and r over 2bk2r epsilon. And that gives us the delta we need. Alright? So we just got it in on one board. Okay, so this finishes the proof. For those of you who didn't vote on seeing all the details in the analysis, I hope you enjoyed this. If not, I hope you learn to be an educated voter in the future. I have handouts on Fourier analysis, which will lead into the quantum mechanics. And so I haven't quite decided yet exactly what I want to do for Fourier analysis in this class. Show of hands again, how many of you have not seen really too much with Fourier analysis in Fourier series? How many of you have seen a lot with Fourier analysis, Fourier series? Convergence questions?
We use them, we don't talk about why.
Oh, you saw them in a physics class! Okay. I remember in my physics class freshman year, my professor wrote a formula on the board and said, in a math class, it would take, you'd spend 6 weeks justifying the following. Moving on, we see the following. And so it's good at least once or twice in your life to see some convergence. I will not do the Fourier analysis in the full generality. and give you the greatest convergence theorems. I will wuss out and take some easy cases where I can show you roughly what's going on and give you a sense. But I will make sure we get to quantum mechanics. Yes?
Nope, we're good.
Okay.
We're good.
Was your answer to yourself worth an M&L? Was your answer to yourself worth an M&L?
Worth the whole pack of it.
Okay, I'll try to remember that. This is the honor system, though, so we're trusting you. Okay. Okay. So, any questions on this? So you can see how crucially we use Cauchy's theorem. This is not a proof that would work in real analysis. Now, maybe there is a different proof you can do that would work in real analysis for differentiable functions. But if so, that's not this one. Okay. So a lot of technical stuff here. And again, the biggest problem is keeping track of where you live. This is why I like to have really good subscripts and keep track of which compact set am I on. For any compact set, I have some choice. How many of you have seen Cantor's diagonalization argument? How many of you have not seen Cantor's diagonalization argument? That basically the real numbers are uncountable.
Oh.
How many of you have not seen the real numbers are uncountable? Right, everybody has seen the real numbers are uncountable. Okay, then I will not go through a proof of Cantor's diagonalization argument, and I will just assume you're all comfortable with Cantor's diagonalization argument. Okay. Alright, so now it's time for Montel 2. Okay, so for Montel 2, this is also known as the Arzelà-Ascoli theorem. So we are now allowed to use Montel 1. So we are now allowed to say that we have a family of functions. If it's holomorphic and if it's uniformly bounded on compactor, then it's equicontinuous. So what we can really do now is to say, well, why don't we just start off with a family of functions that's holomorphic, uniformly bounded, and equicontinuous? Because we know we can do that by Montel 1. So what I want to do, though, is there's a certain word I don't want to use. What word do I want to drop? Holomorphic. Because this is actually a result in analysis. I don't need to use holomorphicity. The proof is not going to require that. So F is a family of equicontinuous functions uniformly bounded on compactor. What's the conclusion from Montel 2? It's what?
Normal.
It's normal. What does normal mean?
Every sequence has a converging subsequence.
Good. Every sequence has a convergent subsequence. And so you should be thinking, some kind of compactness argument as soon as you hear that. So then F is normal, i.e., given a sequence of functions, we have a subsequence that converges. I need a little bit more than just converges. Converges how?
Uniformly.
Uniformly, and where? So how and where? This is like your reporter.
Uniformly
On compactor. That converges uniformly on compactor. Okay. This is where notes would have helped, but okay. We should be able to figure this out, right? We've all read the stuff. I'm supposed to have read the stuff too, right? So proof. And again, I haven't said, of course, what our set is. Our set omega is, as always, open, simply connected. So step 1, there exists a dense sequence of points in omega. Call them the omega n's. So this is where we need a little bit of basic set theory and topology how do I know there exists a dense sequence of points? So what that means is, you give me any point in omega, and there will be a sequence of points from the omega ends that get arbitrarily close. Another way of saying this is, you give me any point in an epsilon, and I can find one of my omegas that's within epsilon of your point. How do you know such a set exists? So this was in the book, they just said take a dense set. Okay, well, how do you know the dense set exists? Oh, the book said it exists.
If it didn't, then there'd be an open ball in the middle of your set, so it would be something like that. So I could find a point that there was no epsilon close point, and I'd have an epsilon ball in the middle of my set.
Excellent. I like that. So, but how does that give you the sequence of points? Because now, okay, so you've now shown me that I can do that, but I have to now build my set of points. You're on the right track.
That's all. Any given ball can just make it really smaller and smaller.
But are we gonna have uncountably many balls? Are you doing this about every point z?
Could do radius 1 over some whatever rational number.
Excellent. Okay. What we want to do is we want to do rationals, but I don't think I want to do balls that are rational. I think I want to do points with rational coordinates. So consider all the points in omega, x plus I, y, where x and y are rational numbers. That's a dense set. And in fact, it's going to be a countable set as well. Okay. So if we use the fact that the rationals are dense on the line, you can show that the rationals will be dense in here as well. And again, if you give me any point, if I draw a small ball about it, there's going to be lots of points with rational coordinates within that. So again, I'm not going to go into the details of this. If you haven't seen counting arguments like this, don't worry. I will not knowingly put an exam question on that. If one of those do pop up, let me know, and I will be very apologetic. Okay? So there does exist something. Use Wn is xn plus I yn, xn, yn, and q. Alright. So you can figure out which ones to take. Alright, so we now have a sequence of points. It's dense. Alright, let's think back to compact sets. Whenever you have a set of points that are dense, what do you immediately start to think about?
The theorem we used.
Which was? I think it was the last thing we got to when we were listing properties of compact sets. And of course the reason is because that's the one I wanted to, so as soon as it was set I stopped. What's a nice property about compact sets? Finite subcover. So what we can do is about each point we can draw a little circle. Right? How big should the circle be? What do we want to make sure we definitely stay inside? Well, not necessarily the compact set. We won't be able to stay inside the compact set. If I take a point on the boundary of the compact set, I have to leave it. It's like, I'm sorry? We want to stay inside omega. Gee, this is looking very familiar. Right? What does this seem a lot like? Montel 1, right? So we could take again, let's let 3r be the distance to the boundary, right? Do all that fun stuff again. Given k, let 3r be less than the distance from k to the boundary of omega. And then draw circles of radius r about each wn. Okay? And if I do that, I'm in great shape. Where will their union live? It'll definitely be in omega. And in fact, it'll live inside what we were calling, Kr or K2r from before. So it'll live inside another big compact set. And what's nice is a finite number of these will cover K. So finitely many cover K live in K2R, say W1, W2, Wj.
Do you know that a finite number cover K2R? Or? So we have that. So we know that K is compact. So
K is compact.
But then do we know that about K2R?
Almost surely you would need infinitely many to cover K2R.
Okay, yeah.
Imagine your K is a circle of radius R,
Right.
and now about over these points, if you draw something of radius 2R, you get a circle of radius 3R.
Right.
And the only way you get this point is to have this point right here. So if you wanted to get all of K2R, you might have to use every single point.
But isn't K2R compact set? So isn't there a finite subcover like that too?
There is a finite subcover, but that's only if I'm covering K2R by open sets. I'm covering I'm covering K by open sets.
Yeah.
So K is covered by open sets, and these open sets move out into KR and K2R, but I'm not covering K2R with open sets. In fact, I'm never even getting to the boundary of K2R. Because when I take anything in K and I draw a circle of radius R about it, I'm not going to hit the boundary. I'll still be at least I units away. So I'm being very careful. I do cover K. It lives inside K2R, but I could actually be a little bit better. It lives inside KR. And a finite subcover of that will work. Okay? Alright, so that's step 2. Step 3, we're now going to start to finally take our sequence and form a subsequence. So I have a sequence of functions. I know my family is equicontinuous. It's uniformly bounded. Does that mean I have a subsequence that converges at W1? So I claim have a subsequence of Fn, call it F1n, that converges at W1. So I'm fixing a special point, and I claim I can take a subsequence of my initial set of functions that's going to converge at W1. Well, think about it. If I've specified the point W1, I now have a sequence of numbers in a compact set. Does a sequence of numbers in a compact set have a convergent subsequence? Yes. This is one of the least popular but equivalent definitions of a compact set. Right? So I know that I can find a subsequence that converges at W1. Okay? So I'll call this 3 prime, have a subsequence of F1n, call it, what do you think we should call it?
F prime.
F2n. That converges where? At W2. All the way down to 3 infinity. Right? Keep going.
I thought you only had finitely many W's.
We only need finally many W's to cover.
Right.
I'm covering my right now and just doing this for all of them.
So when we have to go to 3.
So the question is it enough to just go down to 3j? Possibly. I'm not trying to be as delicate as possible.
Okay, so there could be like.
So it's possible you might be able to stop at 3j.
Okay, but if you go past 3j, what do we have some like fkn that converges to w2 where we already had f2?
Well, so what we do, this initial sequence converges at W1.
Yeah.
The new sequence converges at W1 and W2.
Oh, I see.
Because it's a subsequence of the first sequence.
Right, right.
The next one converges at W1, W2, W3.
But I guess my question is then once you get past J, what? You just
So-
have them all converge to all J all the time, or?
So once you get past J, it's going to be converging out at J plus 1 points. And again, I may not need to do that. I can cover K with finitely many sets. I may be able to stop the argument after J. I'm just being very lazy right now and saying, you know what, why not just give myself more things to look at? And then if we want to, when we finish the proof, we can actually step back and say, was this needed? Because it's a compact set, do I need to do this at all of these points, or is it enough to just do it at some of them? Okay, so now, after 3 infinity, form Gn, which will be Fnn. So, the diagonal sequence. So we take the first term from the first one, the second term from the second one, the third term from the third one, the fourth term from the fourth one. What's nice about this is this will converge at every point W1, W2, W3, W4. If I stopped after J, I would then just take that whole sequence from that point onward. So we're close. We want to show that it's normal so that we have a subsequence that converges uniformly on compactor. We have convergence at all the points we care about, at all the dense points. We now need to go from the dense points to a general point in the set. And we need the convergence to be uniform. Okay? So those are the issues we have. Well, what's nice is we've got fixed points here. Okay. So sadly, I have to erase this. Okay. So what we want to do now is we want to study what's going on at a general point and not just at the points W1, W2, W3, W4. So choose a Z and K. Because Z is in K, what do we know?
It's in one of the balls around one of the other.
Excellent, it's in one of the balls. So there exists a W, and now which W do we assume it's in?
So that sub K? Or no?
So it's in one of the W's. What can you tell me about its index?
Between 1 and J.
Between 1 and J. So now we'll use that. It's in, there exists a WL, L less than or equal to J, such that Z is in the ball of radius R about WL. So here's my WL, here's its ball, here's Z. And what we want to do is we want to basically use compactness. Because we only have finitely many balls, we can do things pretty well. So if we look at at Gn of Z, right? We want to see, does this converge? Okay. So I'm trying to think if I want to just put in my limit function. So I'll subtract off my conjectured limit function. And so I want to look at this. This is where we're going to be adding 0. So what would be a good 0 to add?
Gn of Z of WL and G of WL.
So Gn of Z minus Gn of WL plus Gn of WL minus G of WL plus G of WL, right?
This brings back memories.
And what does your memory call this proof? Sorry?
3 epsilon.
This is a 3
epsilon,
epsilon
yeah.
proof, right? This is the constant we put in these intermediate points. Can we make this small? Can we make this small? Okay, which one of the three is the easiest?
Perhaps the last one.
Oh, I'm sorry, this last one should be a 0.
Yeah, the last one should be.
Okay, why is the last one the easiest? That's not what I would think is the easiest.
The medium one looks calculated.
I'm sorry, I think the middle one is the nicest. Why is the middle one the nicest?
Does it use the same?
That's basically by construction. By construction, we force the middle one to be nice. Now, the middle one is nice by construction. What about over here?
Equicontinuum equal T.
So we know our family is equicontinuous. So given any epsilon, we can find a delta independent of epsilon, depending only on the compact set and epsilon. So this is equicontinuity. Sorry, yes?
Don't we not know that Gn is necessarily equicontinuous? Because we don't know that's one of our functions.
It is.
Didn't we make it out of our functions?
No, we start off with a sequence of functions, and then we take a subsequence of them, call it f1n.
Yeah. But we
sorry,
didn't
f1
pull
and
Gn out of any of those subsequences.
no, Gn is just the diagonal terms. So if you write the sequence as f11, f12, f13,
That sequence.
then we take something from here, and the subsequence of this is the next round. So maybe the first one was f13, the next one was maybe f19, f111. It's still all elements of our original sequence of functions. So Gn is from our list. It's just we've been playing index games up the wazoo. Okay.
Don't we run into the trouble with the last one though, because
So
the
now-
function doesn't have to be in our family?
So now it doesn't have to be enough, but what do we know?
The Cauchy intervals?
Well, now we have one specific function here, g. Right? So we're no longer playing with arbitrary functions, we're playing with a limit function. Let me see how much time is left right now. This is the problem of trying to do this all in one day. We're down to 3 minutes. When this was a Tuesday, Thursday class, this lecture's a lot easier. You know, those extra few minutes makes a huge difference. So, yes?
What are we thinking about G, the first G?
So g is basically like the limit of these functions. Right, so the question is, are we now running into some obstruction here? So can we make this work, or do we have a real problem? So do you remember other ways of finding convergence? Do you remember the Cauchy criterion? So the problem is here is, what do we know about G? What is true on G? So instead of studying Gn of z minus g of z, where g is the limiting function, we can study something like this. Do you remember the Cauchy criterion? So now if we do the Cauchy criterion, what do we get? We get Gn of z minus Gn of wl plus Gn of wl minus, what should this be?
GM.
Gm of wl. And then this would become Gm of wl minus Gm of z. And now if we do that, there's no change here, so that's no problem. By construction, this is fine. It's the Cauchy criterion. Oh, and hey, that's now the same as that one. Okay. So now, so again, a lot of very technical things. It's very easy to subtly assume something about your sequence G. What we've now shown is our sequence has a subsequence that converges uniformly on K. But we want to converge uniformly on all of omega. So we need one more step. And as we have only half a second left, I will just quickly say what the last step is. We do one more diagonalization. For each compact set K, we form a sequence G, and then we use the method of exhaustion. Okay, so you have a sequence of compact sets, K1, K2, K3, K4. Take the first thing from K1. Now look at that whole thing, and the subsequence of that will then converge uniformly on K2. Take something from that, that'll be your second element, and just keep going like that until you exhaust. So now you add one more step, add exhaustion. Alright, so if people want, we can talk a little bit more about it being exhausted on Monday. Get some sleep for that lecture. Okay. If you have any questions, shoot me an email. I have to go